So last time we were talking about virial theorem, like very quickly at the end. Virial theorem is very practical, and we have actually looked at various descriptions of stellar systems, right? The 6-dimensional phase space, the 3D Jeans equation, where you have fields, density field, bulk velocity, and so on. And then virial theorem was like a global quantity. You just calculate total kinetic energy, total uh, potential energy, and then if the system is in steady state, there are certain relations. So there are, depending on the data that you have, you can use whichever model that is feasible. If you don't have very great data, but there are little information about symmetries and so on, virial theorem is all you can do. But if you have Gaia data, for example, you can do this F, the full Jeans equation type, the full Boltzmann equation type evolution, or you can use the Jeans equation. Okay, so today we in a previous class we did these uh, self-consistent potential density pairs, if you remember, like Plummer potential or point mass or constant density distribution, and there was a potential and there was a density distribution that goes along with it. These satisfy the Poisson equation. Okay, but in the 6-dimensional phase space description, you want a self-consistent pair of f, the distribution function, and the potential, right? So it's sort of a similar thing, but we are dealing with the self-consistent distribution function and the potential. So today we'll actually look at a little bit of that. Okay, so self-consistent solutions of CBE, collisionless Boltzmann equation, right? And if you recall, there was this thing we mentioned, there were these Jeans theorems, which said that if you have invariance of motion, like total energy in a time independent potential, or angular momentum and so on, you can write, if you construct a distribution function out of invariance of the system, they are a solution of the collisionless Boltzmann equation. So then there is some strong Jeans theorem which says that you only need three invariants in general to write a well-behaved distribution function, a steady. So in general you can have more than three invariants. For example, for a spherically symmetric problem, not only is your total energy conserved, your three components of angular momenta are also conserved. So there are four invariants of motion, but there is like a theorem. If you assume certain reasonable things, then you don't need to have more than three invariants of motion to have a pretty general description of the distribution function. So let me just write down. So f I1, these are functions of position velocity, I2 position velocity, and I3. This is good enough, right? And if you have a lot of symmetries, you can actually even choose like a constant. You can write a distribution function which is a function of only one invariant, let's say the Hamiltonian. Okay, so that's also fine. But at max, you need three. And this is a mathematical result which I'm not going to prove, but it's sort of given it. So some of this portion on dynamics, Jeans equation, and collisionless Boltzmann equation, I'm actually following Binney and Tremaine. That sort of goes in a little bit more detail than this Gallagher and Spark and Gallagher book. So if you're interested in going into a little more detail, Binney and Tremaine is the book that I recommend. It's a little scary at the beginning, but if you know the stuff qualitatively at the level of what I have actually covered in the class, it will help you navigate that book. Okay. So let's sort of first start with the spherical, spherical system, and let's assume that F is only a function of energy. Right? So energy or the Hamiltonian. Energy is really a constant, but it's really the invariant is the Hamiltonian. It has to be the function of X and V. And this is a good assumption. So it's a good assumption for isotropic objects. It's like spherical objects like globular clusters. Okay, so what are the self-consistent equations that we have? So here we only have I1, essentially, one integral of motion, which is the, in fact, I should really not call it E, it's really the Hamiltonian, because that's the, E is the constant value of that Hamiltonian, but it's really H. Anyway, so what do we have? We have the Poisson equation, which is del squared phi equals 4 pi g rho, and this is actually nothing but 4 pi g integral of f d3v. So here I'm assuming f to be not a probability density, but mass times probability density. It's sort of a trivial interchange between the number and mass. We are assuming that all stars are the same mass, and it's easy to generalize all this. Okay, so this is your Poisson equation. So the particles themselves, the stars themselves, produce the potential in which they move. Okay, so it's like a self-consistent potential F pair. So what do we have? So if you have spherical symmetry, you have DDR. So what is this? R squared d phi dr is equal to 4 pi g integral of f. Actually, let me just, so f v squared by 2 plus potential, which is a function of x, comma r cross v. So this is like the magnitude of potential. So now, I'm actually right. So spherical systems, recall, can have angular momentum too. They are partial by partial phi and partial by partial theta are 0, but they can have velocity anisotropy. If you remember your previous class, we had this beta parameter, which corresponded to velocity anisotropy, and it was a spherical system. So spherical systems can have different radial and tangential velocities if there is a dependence on magnitude of angular momentum. Okay, so this is d3v. All right, but here, like I have said, that I'm just assuming it to be a function of Hamiltonian. Forget about the magnitude of angular momentum. So all angular momentum, all values of angular momenta are equally likely. That's what it means, that there is no dependence on the magnitude of angular momentum. Okay. So in this sort of in these manipulations, it's sort of useful to introduce slightly different variables, psi, which is equal to minus phi plus phi naught, and this is called relative potential. And relative energy, which is nothing but minus E plus phi naught. See, the thing is, for gravitationally bound systems, energy is negative. So you always will see things like square root of minus E. So just to avoid that, we are just doing this almost a trivial change of variables. Okay. So this is nothing but psi minus v squared by 2, right? If this is this, energy is v squared by 2 plus phi. So this is just this. So psi and phi are essentially trivial change of variables. Similarly, this curly E and E are like trivial change of variable. This psi naught is the potential at the edge of the system, right? For example, if you have a potential that sort of looks like this, and if this is your energy of a bound system, all these potentials places is where the particle can exist, right? Because it's a bound particle. So in order for v squared to be positive, this is the only place where your stars can be. If they are, and if they are sort of confined, if they are bound. So in the same way, so this value, this corresponds to phi equals phi naught, or psi equals 0. So this is like the spatial boundary, or the boundary in potential till where the bound particles can exist. Okay. Similarly, this this also corresponds to this is equal to 0, right? So for these particles which are sort of barely confined, right, their E is 0. Below this, capital E is negative, but this curly E is positive. Okay, so this is like trivial. You just have to look at it a little carefully, but that's it. So what you have is F is non-zero only if this curly E is greater than 0, right? Because if you have positive, I mean, if this energy is positive, then your particles are not bound. They'll just leave the potential. If this is negative, that's when this is positive, and then there's this offset of phi naught. Okay, so this F is greater than 0. That is the probability of finding a particle in steady state at that position is non-zero only if it is bound particle. All unbound particles in steady state would have left the system. We are talking about steady state. Okay. And it's 0 if epsilon is negative. So this F is the distribution function. Okay. Let's see. So the Poisson equation in terms of psi becomes minus 4 pi 0, right? In terms of phi, it was plus 4 pi 0, but since there is a negative sign here, it's sort of a trivial thing. Okay, and psi tends to psi naught at the boundary of the system, right? This is sort of the boundary in space, for example, right? The particles can only be within this. So let's look at the Poisson equation. In terms of psi, we have 1 over r squared ddr, r squared psi, sorry, d psi dr. Right, so this is del squared psi is equal to minus 4 pi. So minus 16 pi squared. Let me write down the expression 0 to square root of 2 psi f of psi minus v squared by 2 v squared dv. So what I've done is I've said that velocity distribution is isotropic. F only depends on v squared. So I just change d3v to 4 pi v squared dv. Right. So I have this distribution function is basically the distribution function in velocity space. Okay. Now you have to be careful. This is just F d3v is equal to number or mass is what we are using, mass per unit volume with particles in velocity between v to v plus dv. If you just change this d3v into 4 pi v squared dv. Okay. So this distribution function is defined over velocity. You have to be careful because now we are going to introduce this energy curly E. So the distribution is not function is not relative to curly E. It's relative to V. This you have to keep in mind. This thing is nothing but E, right? This curly E was this only. If you see, go back, this is a curly E. It's basically negative of the energy with this offset of phi naught. Okay. Now since this only depends on curly E, it's better to change the variable from V to curly E. All right, and how do we do that? Right, so we do that from this equation, right? V and curly E are one-to-one sort of variables. So you can do wherever you have V, you can replace it by some function of E. So 2V, so minus 2V dV equals D curly E, right? And if you use that, so you have V dV is dE, but there's an extra V there, you see? And that extra V is just E psi minus curly E 2 times that square root. Right, so let me write that down, and I think this just the right hand side is just minus 16 pi squared. Oh, sorry, I missed G. G integral from 0 to psi. I have done the change of variable to from V to curly E. So this integration goes to this psi. So this F is F E. See, this is what I want you to be careful about. This Fe is written as if it's a distribution function in E space. It is not. It is still this F. All we are doing is just sort of writing it as a function of curly E. Okay, so this times square root of twice psi minus this times d epsilon d curly E. So this is your Poisson equation. 1 by r squared d dr, r squared d psi by dr equals this right hand side. And so E, this curly E is like a velocity. You're integrating over all velocities for this assumption of isotropic distribution. Okay. So you can actually look at it. Then this is your Poisson. So this is if you look at it, so you can actually do two things. So one is given Fe, say Maxwell-Boltzmann or whatever, you can solve for psi, right? So this is a nonlinear equation, right? You see there's a square root of psi appearing here. It's a nonlinear equation for the potential psi given Fe. If you assume an Fe, solve Poisson equation for this psi. Or the second approach is given psi, you solve for Fe. That's also possible. That's an integral equation, right? So given this, you have to somehow invert this equation and get Fe. That's also possible. Okay, so in order to create these self-consistent pairs, you are allowed to use both these roots. In the end, the two equations, the Poisson equation and this equation that rho equals integral of f d3v must be satisfied. So this f is actually a velocity space distribution function. If it is energy space distribution, it's not properly normalized. So now we'll actually do some models. So first we'll do polytropes. Polytropes. So just as in potential density pairs, we are after potential F pairs. And compared to density, F is harder because it lives in velocity and spatial space. Unlike density, which only lives in spatial space. Okay, polytropes. So F, some constant times epsilon. So let me call this curly E epsilon. So n minus 3 by 2, some sort of a power law distribution for energy greater than 0, 0 if this is less than or equal to 0, right? This is just like, just the bound particles. Only the bound particles can achieve steady state. This is the same thing. So this we'll encounter again and again. Right. So rho is 0 where psi is greater than 0, essentially. In other words, there are no particles where energy is positive. They'll just escape. From your previous expression, density is equal to 4 pi integral 0 to infinity f psi minus v squared by 2 v squared dv. Right. And but we know what the value of f is. It's given here. So this is nothing but 4. So substituting this expression for the distribution function, 4 pi capital F integral 0 to square root of 2 psi. Let's see. Right. So v squared, v becomes 0 when psi equals 0. So that's the edge of the system. So this is the limit. So psi minus v squared by 2. So now this is n minus 3 by 2. This whole thing to the power of n minus 3 by 2. This 2 only applies to 3. It's not a bracket. So it's not n minus 3 whole thing divided by 2. V squared dv. Okay. This is just substituting this, and since f is 0, beyond this, you just put this as the limit. Okay, so how do we solve it? We can solve, the integration. So psi for this integral is effectively like a constant, right? Because it lives in x space, not in velocity space. So you can actually do a change of variable. This is a standard integral, right? So if you have a squared minus x squared type of integral, what do? You put x equals a cos theta, right? And then, or you just put it on Mathematica and you get the answer. So the change of variable, if you do, is v squared equals 2 psi cos squared theta. Right. So this is exactly what is the change of variable. And if you integrate, I will not do the integration. Rho, you get rho equals Cn psi to the power of n. So this for psi greater than 0, that's where only there particle can exist. And the Cn is just, I think if you just put it on Mathematica, you will get this. N minus 3 by 2 factorial by n factorial f. This is this f, the normalization condition. So this demands for this integral to converge, this n has to be greater than half for finite Cn. And if n is not integer, this you can actually see even if it is integer, it's a fraction. So it's a gamma function. Yeah, factorial's generalization is the gamma function. So this is the gamma function. So n equal to 0 would correspond to homogeneous density. But that's not allowed here because n has to be greater than a half according to this. So so what do we have? We have the now, so we have obtained rho. Now we have to solve for, so now we have obtained rho in terms of psi. Now we have to solve the Poisson equation, right? So the Poisson equation is 1 over r squared d dr r squared d psi by dr plus so plus 4 pi g rho, right? So 4 pi g cn psi to the power of n. I'm just substituting this equation, right? So this is my Poisson equation. And what we can actually do is we can de-dimensionalize it, or de-dimensionalize. So I mean, basically, de-dimensionalization, what it means is that you just you just say r by some scale length b is you define this as s, some dimensionless scale, and you have psi, small psi, is equal to capital psi by some normalization value of psi. Okay, if you do that, and if you choose your b to be b equals 4 pi g psi naught to the n minus 1 cn to the minus a half. Basically, this you'll get by, I mean, if you do, so this equation is r squared. So if you multiply this by b squared, the whole equation, if you multiply by b squared and divide by psi naught, this becomes dimensionless, right? Because this 1 over r squared and this r squared are canceling on normalizing, but there's a 1 over r squared in the denominator, and then there's a psi in the numerator. If you just do this, these become dimensionless. But the second term will give you, will tell you how to choose your b, so that this also becomes a simple. So this choice of b makes this simple. That is what you have is 1 over r s squared. So Binet and Tremaine is very mathematical. So it's a little difficult. But so astronomy is not just about like waving your hands and stuff. There is a lot of there are a lot of difficult and potentially extremely mathematical areas. So and that's true for all. It's not just GR and cosmology that has mathematical and very subtle things. All areas in astronomy are. It's just that the nature of this area is that observations drive the field. That does not mean that there aren't very theoretical and deep problems. Okay, so if you want to really get an appreciation of the theoretical side of astronomy, I recommend Binet and Tremaine as a book. And if some of your friends tell, oh, astronomy is just about hand waving, just give them that book and they'll realize what they are getting into. So 1 over s squared d ds s squared d psi ds equals, so minus psi to the n. Now this is the de-dimensionalized equation. Okay, so this is a trivial change of variable. This looks like a very nice equation. So this is the nice thing about de-dimensionalization. Things are almost like the equations that you see in your math courses. Okay, all those scary looking things just are hidden behind these constants. Okay, this is called the Lane-Emden equation for self-gravitating polytropes. Right. So, have you guys heard of polytropes? Right. So before uh, people figured out stars, they used polytropic equational state to solve for stellar structure. In polytrope, you assume some sort of a relation between pressure and density so that you can just then solve the hydrostatic equilibrium dpdr equals minus rho g together with that equational state that you assume, right? But modern stellar structure solves the energy equation. You don't assume some relation between P and rho. You put in the fact that energy is produced by nuclear reactions and it's transported through radiation and then convection and all that. So you get the real stellar structure equation. But before this was figured out, people use these simple polytropic models. So this is a second order ODE. For n equal to 0, this is a linear equation, but for other n's, it's a nonlinear equation. Uh, so this is a second order ODE. You need two boundary conditions to solve this, just like as if you do in polytropes. Okay, so the natural boundary conditions are at r equal to 0, say psi equals 1. In that case, what you're saying is psi is the value of the potential at r equal to 0, and say d psi ds equal to 0. Basically, this is like the force vanishes at r equal to 0. The gravitational force at r equal. So this is a set of boundary conditions. If you start with this, you can just solve this. Analytically, you cannot solve it for all n's, but numerically you can. Okay, let's see. So let's actually talk about polytrope gases. So this is P equals K rho to the gamma, dP dr equals minus rho G equals minus rho d phi by dr. If you substitute this here in pressure, what do you get? You get gamma K rho to the gamma minus 2 d rho dr equals minus d phi dr equals minus g m. So for a spherical system, this is the gravitational force. This is equal to d psi by dr. I mean, this is just a trivial change of variable. This can actually be integrated, right? This can actually be easily integrated because there's only rho dependence, and you can trivially do it. What you get is rho to the gamma minus 1 equals k equals gamma minus 1 by k gamma psi, right? This and this you can integrate, and you put this boundary condition that at r equal to 0, psi equals 1. So rho equal to 0 where, or in other words, rho is equal to 0 where psi equal to 0. It's the boundary of the system. So that's why your integration constant would be 0. That's how you have chosen your psi, the offset of your psi. Okay. So if you look at this equation for the gas, and if you look at this equation for your stellar system, right? They look actually somewhat similar. So that was rho equals Cn psi to the n. If you come down, If you compare this equation and that equation, you can actually see that gamma is equal to 1 plus 1 by n. This is the polytropic index. I don't know. Polytropic index. I mean, both of them are actually called polytropic index. So, gamma and n, there is a relation between them. So that's why, they are essentially the same systems, because you get a similar looking equation. This equation and this equation are the same essentially. So the density distribution of the stellar polytrope of index n is the same as polytropic gas sphere with gamma equals 1 plus 1 by n. We have actually shown this here. You cannot solve this Poisson equation for general n. This cannot be solved for a general n. It can be solved for a few values of n analytically. Yes, analytically is what I meant. Yes. And so for n equal to 5, you can solve it. And n equal to 5 is the Plummer sphere. Okay. And so the solution is psi equals 1 over 1 plus s squared by 3, square root of that. Now, if you do 1 by s squared dds, this is that dimensionless Poisson equation, s squared d psi by ds. If you just plug that in, what you get is minus 1 by 3 s squared dds of s cube by 1 plus s squared by 3 to the power of 3 by 2. I mean, it's just algebra, which I'm not going to do. I mean, you have to take the derivative of this, and this is actually equal to minus 1 by 1 plus s squared by 3 to the power of 5 by 2, which is nothing but minus psi to the power of 5. Right? This is psi. This is minus psi to the power of 5. And what we have is this satisfies the Poisson equation for n equals 5, this polytropic Poisson equation for n equal to 5. So your density is equal to C5 times psi to the power of 5, which is equal to C5 by 1 plus s squared by 3 to the power of 5 by 2 psi naught to the power of 5. You see, this is Plummer density 1 over 1, 1 by a squared plus r, or it's sort of like 1 over 1 plus r squared by a squared to the power of 5 by 2. Right? This was your density for a Plummer sphere. For a Plummer sphere, the total enclosed mass integral of 4 pi r squared rho dr 0 to infinity is a finite number, but the density does not have a cutoff. Density keeps on decreasing at large r. It does not become 0 at some finite r. Okay, so this is what Plummer, and it's a good fit for. So for n equals 5, you see this is e to the power of 5 minus 3 by 2. That seems to be a good fit for globular clusters. Okay, in fact, we had actually, when we talked about Plummer sphere in the density potential pairs, we actually said that this is a good model for spherical systems like globular clusters. Okay. So these models can be solved numerically for different n. So let me actually, so for n less than 5, Rho goes to 0 at finite R, right? So they are more concentrated for n less than 5. So n equal to 5 is of course Plummer. And of course, if rho goes to 0 beyond a finite R, total mass is constant. Similarly, this one we just showed that although rho does not become 0 at any finite R, the total enclosed mass becomes a constant. For n less than 5, for n greater than 5, you have rho falls slowly. So rho falls slowly, and in this case, enclosed mass tends to infinity as R tends to infinity. This is like your NFW potential or your isothermal sphere. All those have this property. These are extended potentials n greater than 5. So for dark matter halos, you need these kind of potentials so that you get flat rotation curves. Flat rotation curves have m is proportional to R, right? So that m by R, which is like Vc squared, the circular velocity squared, is a constant. So these are good. These kind of models will be good for dark matter halos, extended potentials. So what about isothermal? So sometimes for dark matter, we use isothermal sphere. Today, internet is actually good. Last time it was so bad. So isothermal sphere, right? Remember, gamma equals 1 plus 1 by n. Gamma equals 1 for isothermal equation of state. So n going to infinity is your isothermal polytrope, or P equals K rho. So if you go to the gas limit for the gas, of course, this is dpdr equals kt by m d rho dr, right? This is just hydrostatic equilibrium. T is the isothermal temperature of the gas. M is the mass of the particle. This is your hydrostatic equilibrium. And this is nothing but minus rho g m enclosed by R squared. This is just dpdr, and this is minus rho g. So, and T is constant. Isothermal means that the temperature is constant. So this is an easy thing to integrate. Minus rho by R squared g times 4 pi R prime squared rho R prime dr, right? That's just m enclosed dr prime. So this is the left hand side, and this is the right hand side. So you just take R square on that side and 1 by rho on the left hand side. What you get is ddr of R squared d log rho dr. Right? There is d rho dr, and then there's 1 by rho that comes in the left, is equal to minus g m by kbt. Kb is the Boltzmann constant, right? So this k is kb. 4 pi R squared rho. Right. So this is the isothermal Lane-Emden equation. This can actually also be solved numerically. Now for the right, so for other n's, for the other power law distribution functions, we got these different polytropes. But what about for n going to infinity? You cannot apply that formula for n going to infinity. So that's the special case. The isothermal case is a special case. And for this, uh, our distribution function is actually equal to Fe is equal to rho 1 by 2 pi sigma squared 3 by 2 e to the e by sigma squared. So this is like a Maxwell-Boltzmann distribution function uh, in uh, in velocity. So this is, I'm just sort of giving you this as a fact, but for a so this is not a power law. So the isothermal limit does not give you a power law, but an exponential, this Maxwell-Boltzmann distribution of energies or velocities. And that's nothing but rho 1 by 2 pi sigma squared to the power of 3 by 2 e to the power of psi minus v squared by 2. That's nothing but epsilon by sigma squared, right? And this sigma squared is your velocity distribution, right? Velocity, yeah. This is your velocity dispersion. This is similar to your Maxwell-Boltzmann, right? This is the Boltzmann factor. The probability distribution is proportional to e to the minus energy by kT. And energy is v squared by 2 plus phi. So that's just equivalent to kT by m for the gas system. Sigma squared is kT by m. For if you were sort of thinking about the gas. So what about the density? So again, if we have F epsilon or Fe, we can get the density by integrating over all velocities or energies. Your rho is equal to integral Fv 4 pi v squared dv. And this is your Fv. And if you integrate it, you just get rho 1 e to the psi pi sigma squared. Right, because this e to the minus v squared by 2 sigma squared dv, this whole thing is a normalized Gaussian. If you integrate it over, you get 1. So this is the density of an this is the mass density in an isothermal sphere with this PDF. So what do you see? So this psi is large where potential is small, right? So let's go back to this figure. This is where the particles are. So the particles will be most likely be here because this is the lowest energy. So all particles are able to go there. Only whereas here at the edges of the system, only the highest energy particles are able to go. Right? So the density is highest where the potential is the minimum or psi is the maximum that you see in that distribution in that row, right? Wherever this is maximum, you have a larger density. I mean, sort of, this is consistent with your, Boltzmann factor. This is exactly what you would expect in equilibrium systems, but the dark matter is not equilibrium. This is just by chance you get the same distribution function. This is not a necessary requirement for collisionless systems. That's what makes the collisionless systems hard, because they can have like infinite solutions with different distribution functions. Okay. But this is also a good distribution function. Okay, let's see. So what is the Poisson equation then? The Poisson equation is ddr 1 by r squared d psi by dr equals minus 4 pi g rho. We already solved for rho here, so that's just minus 4 pi g rho 1 e to the psi by sigma squared. You see, this equation looks different. So in the previous case, when we are doing general polytropes, you had a psi to the some power. Here you have e to the power of psi. So this is actually the difference. And if you actually look at the gas equivalent of this, where did it go? Here, this is your gas system. Right, so d log rho by dr is nothing but psi by sigma squared, right? Because if this is rho, d log rho by dr is psi by sigma squared, or 1 by sigma squared d psi by dr, basically. So then if you just compare this and this, you can read off the relationship between sigma squared and kt. So, basically sigma squared equals kbt by m, right? So, because if you plug this rho into that equation, right, you will get the same equation, except that there you have t, here we have sigma, and if you just compare the terms, you'll get this. And this makes sense. Sigma square is your velocity distribution, the width of your velocity spread. And temperature is nothing but a measure of kinetic energy per particle. So, it's not a surprise that the two come out to be the same. Okay. So as I mentioned previously, the Maxwellian distribution is the distribution function in a collisional system, like a dense gas. You always achieve Maxwell-Boltzmann distribution function, but for collisionless system, I mean, it need not be. And for gamma equals 1, the stellar and the gas polytropes have the same distribution functions. But this need not be the case for other gammas. Okay. So what about, so okay, so if these are spherical, the symmetric system, if f is only a function of energy, we expect the mean velocity to be 0, right? We are only assuming it to be a function of v squared, so the odd moment of velocity will be 0. Similarly, sigma x squared equals sigma y squared equals sigma z squared from the same fact that from that symmetry, because v squared appears as f is a function of vx squared plus vy squared plus vz squared, so it appears as this combination. Because of that, you can actually prove that prove this. So what about v squared then? V squared is nothing but 0 to for a isothermal sphere or isothermal polytrope. So you have psi minus v squared by 2 by sigma squared v to the 4 dv divided by the normalization 0 to infinity e to the psi minus v squared by 2 by sigma squared v squared dv, right? This is just this is what the definition of moment is. And if you do this integral, the Gaussian integrals are very easy to do. And what you get is just 3 sigma squared, right? This sigma squared is one-dimensional velocity dispersion, right? So whereas this is the sum of this, and this is actually equal to sigma squared. Whereas this v squared is vx squared plus vy squared plus vz squared, and the three of them are equal. So this is 3 sigma squared, and that's why you have, and if you do the mathematics, you get 3 sigma squared. So what about the solution of this equation? Where did that go? This equation. One of the solutions. So of course, this is just the ODE. You need the boundary conditions in order to get the solution, right? But you can actually see that rho proportional to r to the minus 2, rho going like 1 over r squared, is a solution to this equation. If you plug in rho equals k r to the minus 2, you'll see the left hand side and right hand side become equal. And that is called the singular isothermal sphere. This power law solution with rho equals c r to the minus 2 is called a singular isothermal sphere, or SIS. With the c given by sigma squared by 2 pi g. Actually, this you will get if you plug in this form in that Poisson equation. You will, right, if you plug in that rho form in this Poisson equation, you'll get a relation because this left hand side does not depend on c. The right hand side has a c in it, so you'll get c in terms of the other parameters. So this is your distribution function. So rho SIS equals sigma squared by 2 pi g r squared. Is it dimensionally correct? Density, right. So gm by sigma squared is like 1 over radius. It's like Schwarzschild radius. So it's 1 over. So it's 1 over r cube. But where is the mass? No. Mass is also there. It's gm. So you're okay. This is dimensionally clear. So this is the singular isothermal sphere potential. This is a solution for that Poisson equation. So for a singular isothermal sphere, density goes like 1 over r squared. The enclosed mass, which is 0 to r, 4 pi r squared rho dr, is proportional to r. And this gives you the flat rotation curve, right? So this is a good. That's why singular isothermal sphere is a good 0th order model for dark matter halos. It gives you a flat rotation curve. But this is not the only solution. As I mentioned, you need the boundary conditions. So, but if your boundary conditions that you use are rho tilde 0 is equal to 1, this is a d-dimensionalized density. Rho divided by the value of rho at r equal to 0. So rho tilde is that. So rho tilde 0 is 1, and d rho tilde by d r tilde equals 0. Basically, the density is flat at r equal to 0. This boundary condition is not satisfied by this guy, right? Density is not flat at r equal to 0. If you take d rho dr, this blows up at r equal to 0. So this solution does not satisfy this boundary condition. With these boundary conditions, you cannot solve the Lane-Emden equation, the isothermal Lane-Emden equation, analytically. you have to solve it numerically. And the solution actually looks like this. You have a constant value and then the density falls, right? Whereas the singular, so if this is a log-log plot, this is R, this is rho, your singular isothermal sphere sort of goes like this. It goes like r to the minus 2. At large radii, this also goes to r to the minus 2. But at small radii, it flattens because of that boundary condition. Okay. So this is sometimes called a chord isothermal sphere, or yeah, I mean basically it is still isothermal sphere, except that it has a constant density inside. Okay. Singular isothermal sphere. Singular because as r goes to 0, rho is infinite. So SIS is singular isothermal sphere. Now, the problem with singular isothermal sphere is that the density just, the enclosed mass keeps on increasing as you move out. What is the time, by the way? Okay. Good. So there is a generalization, King's King models, not Kings, by King models. So King models are basically using this distribution function to be close to the singular isothermal sphere, but not quite. So let me just write down. So rho 1, 2 pi sigma squared minus 3 by 2 e to the e by sigma squared minus 1 for e greater than 0 and 0 for e less than 0. These are called King models. So this is the same, except for this minus 1 factor. This is the same as this guy, right? The isothermal sphere. Now here, what I've done is just subtracted some a value. So what this does is these are called lowered, also called lowered isothermal spheres. So what you do is you do the same procedure. So density, King density is right. So density is a function of r, but psi is a function of r2, right? So you can actually write density as a function of psi. So this is, so if you just integrate this over 4 pi v squared dv, this, what you get is 4 pi rho 1 by 2 pi sigma squared 3 by 2, 0 to 2 psi exponential psi minus v squared by 2 by sigma squared minus 1 times v squared dv. So what you'll have is, this term was there previously. You'll get something which looks similar, but you have this minus 1 here. That will reduce the density at large radii. Okay, so these are lowered or even called truncated isothermal spheres. So if you look at their densities, these models' densities, they get cut off like this, right? Depending on your sigma parameter, or there is another parameter. But anyway, we don't really have to go into the details of all these different models. Okay, so these are spherical models which are good for spherical systems, but let's see. Right, so these are truncated at something called a tidal radius, RT. And outside RT, there is no mass. So basically, they cut off. Their rho goes to 0 outside this radius. So let's see if we can see it from here. If you integrate this over all velocities, anyway, let's, yeah. So you can actually show that this density goes to 0 at a finite radius, and that radius is called the tidal radius. So we'll not get into this further. Okay, now this is for spherical systems. What about non-spherical systems, right? So this is just to give you a flavor of this. So for example, if you have a disk system, then your distribution function f should be a function of E, but also Lz, right? The z component of the angular momentum. And of course, from the symmetries, we actually also know that VR squared should be equal to Vz squared. Right, but for the neighborhood of the, for the neighborhood of our sun, this actually does not hold. That means the third integral, some sort of a third integral, is also important. It cannot be only a function of E and Lz. Otherwise, the measured random fluctuations in velocity in the radial and vertical direction should have been equal, right? Because of the symmetry, right? This is function of Vx, Vr squared plus Vz squared plus V phi squared. This is only a function of V phi. So the dependence on Vr and Vz appears in the same way. So these have to be equal. But observationally, this is not correct. So there must be a third integral. So let me say some sort of Schwarzschild distribution function. Sometimes for peculiar velocity, peculiar meaning in this case is not Hubble with respect to Hubble. Peculiar here is with respect to the solar motion. For the peculiar velocity distribution in the neighborhood of the sun, sometimes people use the Schwarzschild distribution function, which is Fv d3v equals n naught d3v by 2 pi to the 3 by 2 sigma r sigma phi sigma z. So you assume the velocity ellipsoid to be aligned with r phi and r phi and z directions, and you assume the velocity distribution in those three directions to be Gaussian. So this would be minus Vr squared by 2 sigma r squared plus V phi squared by 2 sigma phi squared. This V phi is only the fluctuations about the mean motion. This V phi is not the actual V phi. It's the peculiar velocity plus V z squared by twice sigma z squared. So Schwarzschild is better than this assumption because this gives you this, but the observed velocity distribution for this and this are different. So that's why you use this. So, you use the the distribution function which is consistent with all the observations that you have. For example, so if you have a spherically symmetric system, so spherically symmetric system, but where f is a function of not only E, but also the magnitude of L. And magnitude of L is an integral of motion. Now this is nothing but R times V theta squared plus V phi squared. Right, so here sigma theta and sigma phi have to be equal, but sigma r need not be. Now in this case, you can choose some sort of a distribution function which is a function of energy and L. L is this magnitude of L, which you can actually choose as F king, say for example, king profile as a function of energy times exponential minus L squared by twice sigma squared RA squared, something like this. So what are you doing? So in the energy space, you have the same distribution function as the king or say singular isothermal sphere. But in momentum, what you're doing is you are suppressing the number of stars which have high L. High values of L are exponentially rarer in this distribution function. So it's a spherical system. So what do you, so this would be like, you know, you have a spherical system. So some orbits are like this, some are like this, some are like this. Individual orbits have angular momentum, but all these orbits are equally likely. So as a system, it does not have a net angular momentum. That's why it sort of describes a spherical system. But you know, if you have these stars which are at larger radii, these in general will have larger L, right? What it says is as you go, you know, at large radii, where particles or the stars have large magnitude of angular momentum, the distribution function is suppressed. Or at large radii, you have mostly radial orbits. You don't have large angular momentum because the large, if you had an orbit which was like this, it would have very large angular momentum. But that is exponentially suppressed. So what this sort of shows a system which has at small scales, it has almost almost equal spread in tangential velocities and the radial velocities. But as you go to larger and larger scales, they become more and more eccentric. The orbits of individual stars become more and more eccentric because eccentric orbits have low angular momentum, right? So this is so this actually applies to elliptical galaxies and other spherical systems which have this beta not equal to this. There was this anisotropy parameter, if you remember. As you go to larger and larger radii, the particle trajectories become more and more radial. Good. So if, I mean, RA is like a parameter. If RA is big, right, this transition from isotropic orbits to these anisotropic orbits happens at larger radii. Right? It's sort of a parameter. It depends on what system you're talking about, because L is a specific angular momentum, so it's velocity times R. So R is sort of just to normalize that. This is appearing. What about say a disky system? Disky system. If you have a disky system, you can actually imagine your F. In that case, you have Lz as a conserved quantity. Your F can be function of E and Lz, which is equal to say F tilde E, some energy dependence, and then you have some dependence on LZ. You know, this is separable. But say for a disk galaxy, most stars are almost on circular orbits with high angular momentum. So this function should be an increasing function of LZ, so that you suppress the stars which are on purely radial orbits. So this should increase with the magnitude of LZ up to the sort of maximum angular momentum, and then dip. So so these are kind of things that people use. You look at the system that you're describing and try to guess what sort of distribution function can it have. Let me actually show you a few things. Right. So I had mentioned to you guys about this asymmetric drift in the last class, that from this genes modeling, you can get this, right, because of spread in radial, so because of random motion in the radial direction, VR squared bar not being zero, the stars are not moving at the circular velocity. They are moving slightly slower than the circular velocity. You can actually think of it as support against gravity due to pressure. So this actually shows the data for that asymmetric drift. So this is from our book, from Spark and Gallagher. This is dispersion and velocities Vx and Vy. So this Vx and Vy is measured relative to the local standard of rest or something. For F and G dwarfs near the sun increases with age. So these are younger stars. So you can actually see the spread in the velocities are smaller. Just by eye, you can actually see smaller than these. So dwarfs are like main sequence stars. These guys have larger spread. The youngest stars show a vertex deviation. So the median of this is somewhere here, no? And the median of this is somewhat lower. So those stars have not yet had time to move away from the groups in which they were born. Anyway, the average value of Vy is increasingly negative for older stars. These are the older stars, and the mean value of Vy here is lower than the mean value of Vy here, is what the caption is saying. So this is what that expression for asymmetric drift was. This Va was proportional to VR squared bar. If your random motion in the radial direction is higher, which is the case for this, then your lag from the circular, test particle motion will be higher. So this is actual data.